Chemical properties and compounds subgroup 15 elements. Okay. Chemical properties and compounds subgroup 15 elements. Okay. Elements in standard state as less reactivity, particularly due to multiple bonding in nitrogen and greater atomic phosphorus, arsenic and bismuth. Antimony. Okay. First point, chemical reactivity. Chemical reactivity. Okay. Nitrogen is gaseous and diatomic. Nitrogen is gaseous and diatomic. Nitrogen is gaseous and diatomic. Okay. Nitrogen is gaseous and diatomic. The triple bonded of a nitrogen is very stable. Okay. The triple bond of nitrogen, okay, is very stable. Okay. The triple bonded nitrogen, triple bonded is very stable. Okay. The bond dissociation energy being very high. The bond dissociation energy being very high. The bond dissociation energy being very high, approximately 941.4 kilojoule per mole. Okay. Hence nitrogen is relatively unreactive. Nitrogen is relatively unreactive. Okay. Hence nitrogen is relatively unreactive. Chemically, phosphorus is more reactive than the other elements. Chemically, phosphorus is more reactive than the other elements. More reactive than the other elements. Phosphorus is reactive at room temperature. Phosphorus is reactive at room temperature. Phosphorus is reactive at room temperature. Okay. While the others show reactivity at high temperature only. While the others show reactivity at high temperature only. Others show reactivity at high temperature only. Okay. Nitrogen combines with oxygen in a small proportion at about 200 degrees Celsius, while other elements form oxides radially, giving P2O5, S2O3 and sp2O3, Bi2O3. Okay. Nitrogen is gaseous and diatomic. Triple bonded nitrogen triple bond is very stable. The bond dissociation energy being very high, 941.4 kilojoule per mole, as nitrogen is relatively unreactive. And chemically, phosphorus is more reactive than the other elements. Phosphorus is reactive at room temperature, while the others show reactivity at high temperature only. Nitrogen combines with oxygen in a small proportion at about 2000 degrees Celsius, while other elements form oxides dually giving P2O5, S2O3, Sb2O3 and Bi2O3. Okay. Second point. Compound formation. Second point, compound formation. Okay. Compound formation. Okay. Second point, compound formation. What is the compound formation? All the elements of group 15 form a covalent gaseous hydrides of the type MS3. All the elements of group 15, all the compound formation. Okay. Compound formation. All the elements of group of 15 form covalent gaseous hydrides of type MS3. All the elements of group 15 form covalent gaseous hydrides of the type MS3. The elements form chlorides of the type MCl3. These elements form chlorides of the type MCl3. In addition, phosphorus and antimony form respectively pentachlorides. In addition, phosphorus and antimony form respective pentachlorides. Pentachlorides PCl5 and SbCl5 Okay. They all form three oxides of the formula. They all form three oxides of the formula M2O3, M2O4 and M2O5. Nitrogen form 5 oxides. Nitrogen form 5 oxides. As example, N2O, NO, N2O3, N2O4 and N2O5. Okay. Third point, hydrides. Third point, hydrides. Okay. Hydrides. All the elements of group 15 form colorless gaseous covalent hydrides. All the elements of group 15 form colorless gaseous covalent hydrides. Colorless gaseous covalent hydrides. covalent hydrides. Okay, these hydrides are ammonia. These hydrides are ammonia. These hydrides are ammonia, NH3 phosphine, PH3 arsine, AS3 stibine, SVH3 and bismuthine. BiS3. These hydrides can be prepared as follows. These hydrides can be prepared as follows. Can be prepared as follows. Okay, prepared as follows. Okay, first is method of preparation. Method of preparation. Okay, when binary metals or compound Mg3N2, Mg3Sb2, Mg3Bi2 react with water or dilute acids, then MS3 type of hydride is formed. MS3 types of hydride is formed. Okay. Method of preparation. Okay. Method of preparation. When binary metals compounds magnesium. Binary metals compound Mg3N2, Mg3Sb2, Mg3Bi2 react with water or dilute acids. React with water or dilute acid. Then MS3 type of hydride is formed. Then MS3 type of hydrides are formed. Okay. Mg3N2 plus 6H2O. That makes 3 NaOH whole twice plus 2NH3 ammonia. Okay, and Ca3N2 plus 6H2O. That makes 3 CaOH whole twice plus 2NH3 and Ca3P2 plus 6H2O. That makes 3 CaOH whole twice plus 2PH3 and Zn3AS2 plus 6HCl. That makes 3 ZnCl2 plus 2AsH3 and Zn3M3 plus 6 HCl that make 2MH3 plus 3ZnCl2 where M equal to arsenic, antimony and bismuth. Okay. The most important hydrides of nitrogen NH3 is prepared by Haber process at industrial level. Okay. The most important hydrides of nitrogen. Hydrides of nitrogen NH3 is prepared by Haber process at the industrial level. Okay. Properties of hydrides. There is regular change in the properties of MH3 type hydrides, which is explained as follows. First point. All hydrides are foul smelting gases and soluble in water. Okay. All hydrides are foul smelling gases and soluble in water and soluble in water. Okay. All hydrides are foul smelling gases and soluble in water. Second point. Pyogeneous nature. Okay. All the hydrides except ammonia NH3 are poisonous. All the hydrides except ammonia. All the hydrides except ammonia are poisonous. Ammonia are poisonous. Except ammonia are poisonous. Ammonia is also harmful. Ammonia is also harmful on excess breathing. Okay. Third point. Melting and boiling point. Melting and boiling point. Okay, third point, melting and boiling point. The melting and boiling point value increases from the melting point and boiling point, the melting point and boiling points value increases from boiling point value increases value increases from phosphine to pH3 to BiH3. The melting and boiling point value increases from pH3 to BiH3. In pH3, the interaction between molecules is van der Waals forces. The interaction between molecules is van der Waals. Molecules is van der Waals. Van der Waals forces due to which van der Waals forces due to which its melting point and boiling point's value is lower. Its melting point and boiling points values are lower. Okay. Boiling point and melting points increases and moving down the group because of increment in molecular size from pH3 to BiH3. Okay. Boiling point and melting point increases and boiling point and melting point. Boiling point and melting point increases and moving down increases and moving down the group because of increment in molecular size. Because of increment in molecular size. Increment in molecular size from pH3 to BiH3. Okay. Association. Next point, association. Okay. Next point, association. Okay. Association. 1 minute. Association. Next point, association. Next point, association. Only the hydride of nitrogen NH3 associate due to hydrogen bonding. After hydrides do not undergo the process of association. Only the hydride of nitrogen only the hydride of nitrogen is that NH3 ammonia associates due to hydrogen bonding due to hydrogen bonding. Other hydrides do not undergo the process of association. of association, process of association, undergo the process of association. Okay. Fifth point, hydrogen bonding. Hydrogen bonding. Sixth point, hydrogen bonding. Okay. Due to electronegativity difference, there is a charge separation. Due to electronegativity difference, there is a charge separation. Nitrogen, hydrogen, and plus delta hydrogen, and this is hydrogen plus delta, that is minus delta. Okay. Due to charge separation, position end of one molecule is attracted by negative end of the other molecules as nitrogen minus delta hydrogen, and hydrogen plus delta, that is hydrogen bond, that is hydrogen bond. Okay. And nitrogen minus delta hydrogen plus delta nitrogen minus delta hydrogen, that is hydrogen plus delta. Okay. This is known as also hydrogen bond. Okay. Due to charge separation, positive end of one molecule is attracted by negative end of the other molecules. Okay. Negative end of the other molecules. Okay. Thus, ammonia behaves as polymers. Thus ammonia behaves as a polymer. Ammonia behaves as a polymer. Its molecular weight is high, and hence boiling point is also high. Okay. Its molecular weight is high. Its molecular weight is high. Its molecular weight is high. And hence boiling point, boiling point is also high. As electronegativity difference between phosphorus and hydrogen, as electronegativity difference between phosphorus and hydrogen, is low, and the size of phosphorus and size of phosphorus is large. Okay. No hydrogen bond occurs in phosphine. No hydrogen bond occurs. Hydrogen bond occurs in phosphine. Okay. Similarly, AsH3, SbH3, and BiH3 H3 do not show hydrogen bond. Do not show hydrogen bond. Okay. 6 point. Thermal stability. Thermal stability. Thermal stability. Okay. The ammonia behaves as a polymer. Its molecular weight is high and hence boiling point is also high, as electronegativity difference between phosphorus and hydrogen is low and the size of phosphorus is large. No hydrogen bond occurs in pH3 phosphine. Similarly, ASH3, SbH3, BiH3 do not show hydrogen bond. Okay. Thermal stability. Okay. Thermal stability. Next, thermal stability. Okay. Thermal stability. Okay. The stability of this hydrogen decreases from ammonia to BiH3. Okay. Thermal stability. NH3 is the greater than pH3 is the greater than ASH3 is the greater than SbH3 is the greater than BiH3. Okay. Okay. The stability of these hydrides decreases from NH3 to BiH3. Okay. As metallic character increases, thermal stability decreases. As metallic character increases, thermal stability decreases. Thermal stability decreases. Thermal stability decreases. Okay. Decreases. The stability of hydrides can also explain with the help of their decomposition temperature. Okay. The stability of hydrides can also explain with the help of their decomposition temperature. NH3 1300 degrees Celsius, pH3 400 degrees Celsius, and ASH3 280 degrees Celsius, and SbH3 150 degrees Celsius, and BiH3 high unstable. Okay. The stability of hydrogen decreases with the rise in atomic weight. Nitrogen forms the most stable hydride NH3, while bismuth BiH3 is least stable hydrides, and decomposition evolve hydrogen gas. Okay. MH3, that is delta M plus 3 by 2 S2. Okay. Next point, reducing character. Okay. Reducing character. Okay. As we move down the group, reducing character increases from NH3 to BiH3. Okay. As we move down the group, reducing character, as we move down the group, reducing character increases from NH3 to BiH3. Okay. NH3 is the less than pH3 is the less than ASH3 is the less than SbH3 is the less than BiH3. H3. Okay. As metallic character increases, as metallic character, as metallic character, metallic character, as metallic character increases, as metallic character increases, the reducing power of MS3 increases. Reducing power of MS3 increases. Okay. Reducing power of MS3 increases. Thus the hydride of nitrogen. Thus the hydride of nitrogen is that ammonia. NH3 is a weak reducing agent. Weak reducing agent, while bismuthine BH3 is the strongest reducing agent. Is the strongest reducing agent. Is the strongest reducing agents. Okay. As metallic character increases, reducing power of MS3 increases. Okay. As metallic character increases, reducing power of MS3 increases. Thus the hydride of N2 ammonia NH3 is a weak reducing agent, while bismuth is the strongest reducing agent. 8 point. Basic character. Okay. Point 8. Basic character. Hydrides of all these elements are basic since they are proton acceptors. Okay. Hydrides of all these elements are basic since they are proton acceptors. They are proton acceptors. Basic character decreases from basic character decreases from nitrogen to bismuth. Okay. Basic character of the hydrides decreases as shown in the below. NH3 is the greater than PH3 is the greater than AH3 is the greater than SbH3 is the greater than BiH3. Okay. Basic character. Hydrides of all these elements are basic since they are proton acceptors. Basic character decreases from nitrogen to bismuth. Okay. All hydrides contain a lone pair of electrons in their central atoms. Okay. Hence, all these hydrides behaves as a Lewis basis. Ammonia is most basic, while BiH3 is least basic. Ammonia is most basic, while BiH3 is least basic, Okay, least basic. Reaction with water. 9 point. Reaction with water. Reaction with water. Okay. Ammonia is freely soluble in water. The resultant solution is NH4OH, which is a weak base and slightly ionized. pH3 is slightly soluble in water, forming solution which is a neutral. Other are also freely soluble in water. Okay. Ammonia is freely soluble in water. Ammonia is freely soluble in water. Soluble in water. Ammonia is freely soluble in water. pH3 is slightly soluble in water. pH3 is slightly pH3 is slightly soluble in water. Slightly soluble in water, forming a solution which is neutral. Forming a solution which is neutral. Solution which is neutral. Okay. Which is neutral. Others are also freely soluble in water. Others are also freely soluble in water. Okay. Soluble in water. Okay. 10 point. Complexing agent. 10 point. Complexing agent. Okay. Ammonia acts as a complexing agent due to donation of one pair of electrons to others. Okay. FeCl3 plus 3NH4OH that make FeOH whole thrice plus 3NH4Cl. Okay. And AgCl plus 2NH4OH that make AgNH3 whole twice Cl plus 2S2O. Okay. pH3 AsH3 SbH3 and BiH3 precipitate metals like precipitate metals like silver and copper as phosphide, arsenide, antimonide and bismuthinide. Okay. 3CuSO4 plus 2pH3 that Cu3P2 plus 3H2SO4. Okay. 3AgNO3 plus SbH3 that make Ag3Sb plus 3HNO3. Okay. Next, shape and structure. Okay. Shape and structure. shape and structure. Okay. All the hydrides show sp3 hybridization, hence their structures are tetrahedral. Their structures are tetrahedral. But all contain one pair of electrons, hence they have a pyramidal shape. Okay. But all contain one pair. All contain one pair. All contain one pair of electrons. One pair of electrons. Hence they have a pyramidal shape. Okay. This is clean from the shape and structure of ammonia. You can show 1s, 2s, 2p. Okay. That is 1s, that is 2s, and that is 2p. That is 2p. Okay. N atom in ground state. N atom in ground state. Okay. Then that is sp3 hybridization. sp3 hybridization. Okay. sp3 hybridization. Okay. That is nitrogen that is hydrogen, and that is hydrogen. Okay. That is hydrogen. Okay. That is pyramidal shape. Pyramidal shape. That is pyramidal shape. Okay. Hybridization of ammonia in NH3 sp3 hybridization. Thus there are 4 sp3 hybrid orbitals, one containing unpaired electrons pair and 3 1 electrons each. 3 sp3 orbitals containing unpaired electrons overlap with 1s orbitals of 3 hydrogen atoms to form 3 sigma bonds. The fourth sp3 orbitals containing lone pairs remains directed towards fourth corner. Okay. Fourth corner of tetrahedron. Thus the structure is tetrahedral and shape is pyramidal. Okay. The bond angle HNH is HNH is 107.3 degree, and the decreases in bond angle from a regular tetrahedral angle is due to one lone pair of electrons present on the central atom nitrogen. According to VSEPR theory, the repulsion between lone pair bond pair is greater than the bond pair repulsion, hence there is a contraction between bond angle. Okay. AS3, ASH3 and SbH3 are the molecules in which central atoms does not hydride. In PS3, ASH3 and SbH3, the hydrogen is almost pure p orbitals of the central atoms and the bond angle is nearly equal to 90 degrees. The lone pair presence as central atom is accommodated in the orbitals having almost pure S character. This lone pair occupies is much more diffuse space which reveals the bonded pair inwards and the bond angle decreases. As the electronegativity of the central atom decreases, size increases, the bond angle decreases. Okay? The bond angle of ammonia is 107.3 degrees, 3 degrees greater than PS3, 99.3 degrees, 3 degrees greater than ASH3 is in bracket 91.8 degrees is greater than SbH3 91.3 degree. The slightly larger angle than 90 degree in PS3 to SbH3 may be attributed due to the interaction between two neighboring hydrogen atoms which occupy a partial charge due to polar bond character. As phosphorus hydrogen bond, arsenic hydrogen bond, etc. bond. As the bond length will increase from hydrogen to Sb, this antimony hydrogen, this results in diminishing the bond angles. Okay. Since the lone pair occupies much more diffuse orbitals, the electron density is very much diminished at PS3, and PS3 loses some of its basic character. Thus PS3 is least basic, has no donor character and not behave as a ligand, whereas NH3 is basic and serves as a good ligand. The important properties of the hydrides are electrical group 15. You can also BiS3 is acidic in character, and nitrogen also form two more hydrides, hydrazine and 2H4, which is basic and hydrogenized acid, and 3A. Phosphorus also form neutral liquid P2S4. Okay. Next point, highlights. Okay. Highlights. Okay. Highlights. All the elements of this group form a trihalide of the formula MX3. Trihalide of the formula MX3. Trihalide. Okay. All the elements of this group form trihalide of the formula MX3. Only NBr3 and Ni3 halides are unknown. Only NBr3 and Ni3 halides are unknown. Halides are unknown. Okay. Halides are unknown. Okay. Halides are unknown. Okay. Only NBr3 and Ni3 halides are unknown. All the elements form a chloride of type MCl3. Okay. MCl3. Okay. All the elements form chloride of the type MCl3. MCl3. Okay. As example, NCl3, PCl3, ASCl3, and SbCl3, and BiCl3, that is nitrogen trichloride, nitrogen trichloride, nitrogen trichloride, that is phosphorus trichloride, that is phosphorus trichloride, that is arsenic trichloride, that is antimony trichloride, that is antimony trichloride, and that is bismuth trichloride, okay. All these chlorides are hydrolyzed by water. NCl3 plus 3H2O, that is hydrolyzed by water. NH3 ammonia plus 3HCl loop, okay, and PCl3 plus 3H2O, that makes H3PO3 plus 3HCl, okay, and ASCl3 plus 3H2O, that make H3ASO3 plus 3HCl, okay. SbCl3 plus 3H2O, that is SbOCl plus 2HCl, okay. BiCl3 plus H2O, that make BiOCl plus 2HCl, okay. NCl3 gives ammonia base. But PCl3 and ASCl3 gives acid in hydrolysis. Okay. SbCl3 and BiCl3 are partially hydrolyzed, okay. Phosphorus, antimony and arsenic form pentahalides like PX5, SbX5, and ASX5. NX5 does not exist, and NX5 does not exist, okay, because covalency of nitrogen is limited to 3. Hence nitrogen and bismuth do not form pentahalide. BiX3 does not exist because +5 oxidation state is not stable due to inert pair effect. As nitrogen does not contain vacant d habitus, therefore pentahalide of nitrogen NX5 does not exist. NX5 also hydrolyzes. Complete hydrolysis of NX5 gives H3PO4, H3SO4 and Sb2O5, okay, and Sb2O5. PCl5, 1 minute. PCl5 plus 4H2O, that make H3PO4 plus 5HCl, and ASCl5 plus 4H2O, that make H3SO4 plus 5HCl, okay, and SbCl5 plus 4H2O, that make H3SbO4 plus 5HCl, Cl. Okay, antimonic acid, that is antimonic acid, antimonic acid. Okay, NCl3 and hydrolysis gives ammonia which is base, but PCl3 and hydrolysis gives H3PO3 which is acid. Nitrogen in NCl3 acts as a donor only, and so in a reaction with water, hydrogen plus water is attached to nitrogen in NCl3. Phosphorus in PCl3 acts as donor and acceptor both. Acceptor due to empty d orbitals, hence it attaches H plus of H2 as well as OH negative of H2O. On hydrolysis, PCl5 first gives POCl3 and HCl, and then POCl3 gives H3PO4. Okay, PCl5 plus H2O, that is POCl3 plus 2HCl, and POCl3 plus 3H2O, that make H3PO4 plus 3HCl. Okay, and PCl5 plus 4H2O, that make H3PO4 plus 5HCl. Okay, also on heating PCl5 also on heating, PCl5 gives PCl3 plus Cl2. Okay, PCl3 plus Cl2. The reaction show that two chlorine atoms in PCl5 are chemically different from the other three. Okay, this has been confirmed by the trigonal bipyramid structure of PCl5, in which two chlorine atoms are axial and three are equatorial. Axial chlorine is more reactive than equatorial, chlorine. In PCl5, phosphorus forms 5 bond with chlorine by sp3 dehybridization. Hence, PCl5 has trigonal bipyramidal geometry with 2 bond angles of 90 degree and 3 bond angles of 120 degree. In case of trihalides of nitrogen and phosphorus, the central metal atom is in sp3 hybridization with 1 lone pair. Hence, trihalide have trigonal pyramidal structure having bond angles less than normal tetrahedral bond angle 109 degree 21 minutes. Okay, the different trihalides have different bond angles as follows. Compound XMX angle, that is NF3 103 degrees, that is PF3 104 degree, that is PCl5 100 degree, that is PBr3 101.5 degree, and that is ASCl3, that is 98.4 degree, and SbCl5, that is 104 degree. Okay, and that is structure, trigonal pyramidal structure of trihalides, that is metals, and double bond, lone pair, and that is X, that is X, that is X. Okay, and phosphorus, chlorine, that is 120 degree, that is chlorine, chlorine, that is 90 degree. Trigonal bipyramidal structure of PCl5, PCl5, trigonal bipyramidal structure of PCl5. Next, oxides. Next is oxides. High point oxides. High point is oxides. Okay, you can show oxides. Okay, oxides. Oxides. This is the 5 point. This is the 5 point. Halides. Okay, halides. 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 Okay, halides. Okay, halides. 1 minute. Oxides. The elements of group 15 form oxide of the type of M2O3. Okay, the elements of group 15 form oxides of the M2O3 type. M2O3, M2O4, M2O5 type. Okay, these oxides are formed by direct or indirect reaction of oxygen with elements of this group. Okay, the difference oxides have you can show. Okay, nitrogen forms 5 different oxides. The acidic character decreases with increase in atomic weight. The oxides of nitrogen and phosphorus are acidic. Okay, the oxides of nitrogen and phosphorus. The oxides of nitrogen and phosphorus are acidic. Phosphorus are acidic. Okay, preparation. Okay, preparation. Okay, the oxides of nitrogen and can be prepared by following methods: NH4NO3, NH4NH3, that is, after heating, this is make N2O plus 2H2 and N2NaNO3, sodium nitrate, plus 2FeSO4, ferrous sulfide, plus 3H2SO4, sulfuric acid, that react and make Fe2SO4 whole thrice, plus 2NaHSO4 sodium bisulfate, plus water, plus A2NO sodium monoxide. Okay, this 2NO is react with N2O4. React with N2O4 at 250 degree Kelvin temperature, that make N2O3. Okay, and 2BNO3 whole twice at 673 Kelvin temperature, that made NO2 plus 2BO plus O2. oxide at cold N2O4 and 2HNO3 plus P2O5 at hot that make 2HPO3 plus N2O5. Okay, these oxides of phosphorus third, arsenic third and Sp third can be prepared by heating in presence of oxygens. Okay, the oxides of phosphorus, arsenic and Hb, antimony can be prepared by heating in presence of O2, that is 4 phosphorus plus 3 O2 that make 2P2O3 and 4 arsenic plus 3 O2 at heating at a temperature that make 2AS2O3. Okay, phosphorus pentoxide can be prepared by burning white phosphorus in presence of air or oxygen. Okay, 1 minute. Phosphorus pentoxide can be prepared by burning white phosphorus in presence of air or oxygen. Okay, P4 plus 5O2 that make P4O10 plus 71 kilocalorie. Okay, and P4 plus 10CO2 that make P4O10 plus 10CO carbon monoxide when P2O3 is heated. P2O3 is heated in a closed tube then P2O4 is obtained. Then 4P2O3 that 3P2O4 plus 2P. Okay, that is a phosphorus tetroxide. phosphorus tetra oxide, no, phosphorus pentaoxide is clear, phosphorus pentaoxide, phosphorus pentaoxide, pentaoxide, okay. Phosphorus pentaoxide can be prepared by burning white phosphorus in presence of air, okay, and P4O10, 5 multiple of 5, oxygen in multiple of 5, so this is known as penta, okay, pentaoxide. And properties. The oxides of nitrogen and phosphorus are acidic and form acids by dissolving in water. Okay? The oxides of nitrogen and phosphorus are acidic and form acids by dissolving in water, dissolving in water, okay, water. N2O3 plus H2O, that make 2HNO2, okay. This is nitrogen trioxide, this is nitrogen trioxide, and that is nitrous acid, HNO2, nitrous acid, okay, nitrous acid, okay. And N2O4 nitrogen tetraoxide, this is nitrogen tetraoxide plus H2O, water, that make HNO2 nitrous acid plus HNO3 nitric acid, nitrous acid plus nitric acid, okay. N2O4 plus H2O, nitrous acid plus nitric acid, okay. This is nitrogen tetraoxide, nitrous acid and nitric acid, okay. And N2O5 nitrogen pentaoxide, nitrogen pentaoxide plus H2O, that make 2HNO3, okay. 2HNO3, okay. 2HNO3. And P2O3 plus 3H2O, that make 2H3PO3, phosphorus acid, that is phosphorus acid, H3PO3, phosphorus acid, okay. This is phosphorus acid. P2O4 plus 3H2O, that make H3PO3 plus H3PO4, phosphoric acid. This is phosphoric acid, this make phosphoric acid. And P2O5 plus 3H2O, that make 2H3PO4. The The oxide of arsenic, antimony and bismuth are amphoteric in nature. They react with alkalis to give arsenides, antimonides and bismuths respectively. With dilute hydrochloric acid they give salts like ASCl3 and SbCl3 and BiCl3. M2O3 is acidic. The order of acidic character is as the order of acidic character. The order of acidic character is as 1 minute. 1 minute. 1 minute. The order of acidic character is as N2O3 is greater than P2O3 is greater than AS2O3 is greater than Sb2O3 is greater than Bi2O3. This is the order of acidic character. Order of acidic character. Order of acidic character. This is the order of Sb2O5 and acidic character decreases, okay? And N2O3 and P2O3 are acidic. AS2O3 and Sb2O3 are amphoteric, okay? This is N2O3 and P2O3 are acidic. P2O3 are acidic, okay? Acidic. And AS2O3 and Sb2O3. AS2O3 and Sb2O3 are amphoteric, amphoteric. And Bi2O3 is basic, okay? As a non-metallic character decreases, acidic character decreases, okay? As a non-metallic character decreases, acidic character decreases. M2O5 is also acidic. M2O5 is also acidic. M2O5 is also acidic. The order of acidic character. The order of acidic character. N2O5 is greater than P2O5 is greater than AS2O5 is greater than Sb2O5 is greater than Bi2O5. This is insoluble in water. Sb2O5 and Bi2O5. Sb2O5 and Bi2O5 is insoluble in water, okay? As stability of +3 oxidation state increases, thermal stability of M2O3 type oxides also increases, okay? This is the N2O3 is the less than P2O3 is the less than AS2O3 is the less than Sb2O3 is the less than Bi2O3. As stability of +3 oxidation state increases, thermal stability of M2O3 type oxide also increases, okay? Thermal stability. This is the thermal stability, order of thermal stability. This is the order of thermal stability, okay? As stability of +5 oxidation state decreases, thermal stability M2O5 increases. As stability stability as a stability of plus 5 oxidation as stability of plus 5 oxidation state decreases. Oxidation state decreases thermal stability of thermal stability of M2O5 increases N2O5 M2O5 increases and N2O5 is exception. Okay. Then N2O5 is less than P2. P2O5 is less than AS2O5 is the N2O5 is less than and greater is the AS2O5 and AS2O5. Okay, greater is the AS2O5 and AS2O5 is less than SB2 is greater than SB2O5 is greater than Bi2O5. Okay, RM2O5 are strong oxidizing agent. All M2O5 are strong oxidizing agent. Strong oxidizing agent. Okay, P2O5 is non-oxidizing agent, and P2O5 is a non-oxidizing agent. Okay, oxidizing agent. And structure of oxides. Structure of oxides. Okay, structures of oxides. Okay, structure of oxides. Then first nitrous oxide. IR spectra and X-ray studies show that nitrous oxide N2O molecule is linear and asymmetrical. Its dipole moment value is very low, 0.11 D. It is called as a laughing gas. It is called as laughing gas. It is a resonance hybrid of the following structures. It is resonance okay, it is resonance hybrid of the following structure. Resonance hybrid of the following structure. Okay, of the following structure, that is nitrogen negative, double bond nitrogen positive. This is first equal to oxygen, double bond oxygen, and nitrogen triple bond nitrogen plus and oxygen is combined with a single bond. And this is second figure. And third number nitrogen double bond nitrogen 1 2 3 4 5 6 and 2 negative, nitrogen positive, triple bond, oxygen positive. This is the odd number. Okay. This is structure of laughing gas. Laughing gas is also known as nitrogen oxide, nitrous oxide. Nitrous oxide is also known as laughing gas. Okay. In a nitrous oxide molecule, the bond distance between nitrogen and nitrogen-oxygen bond distance in nitrous oxide molecules, the bond distance between nitrogen and nitrogen oxygen is 1.126 angstrom and 1.191 angstrom respectively. Okay, respectively. Okay. Next, nitric oxide. Second, nitric oxide. Structure of nitric oxide. Okay, structure of nitric oxide. Okay, structure of nitric oxide. Second point, nitric oxide. Structure of nitric oxide. NO, nitric oxide, NO. Nitric oxide, NO, nitric oxide. Okay, structure of nitric oxide. Nitric oxide is a odd electron molecules having 11 electron outermost orbit. That is nitrogen 1, 2, 3, oxygen. Okay. Nitric oxide is a odd electron molecules having 11 electron outermost orbit. Nitric oxide NO has one sigma bond. Has one sigma bond and one pi bond and one 3 electron pi bond and one 3 electron pi bond. Okay. Due to presence of 3 electron bond, nitric oxide is odd electron molecules and is paramagnetic. This is paramagnetic. Okay. The nitrogen oxygen bond distance in NO monomer is 1.15 angstrom. The bond distance of nitrogen oxygen bond is 1.15 angstrom. Nitric oxide monomer is 1.15 angstrom, which lies between double and triple bond. According to this, it occurs in resonating structure as nitrogen, double bond oxygen, arrow mark of nitrogen 1, 2, 3, 4 and 1 negative, double bond oxygen 1 positive, 1, 2, 3, and that make nitrogen 1, 2, 3 plus and oxygen 1, 2, 3, 4, 5, 6 and negative. Okay. In liquid and solid state, it shows diamagnetic properties. Okay. In liquid and solid states, in liquid and solid states, it shows diamagnetic properties. It shows shows diamagnetic, diamagnetic, diamagnetic properties, okay, diamagnetic properties. This is due to its association properties, nitrogen, single bond nitrogen, okay, and double bond with oxygen, 1 2 3 4, and double bond with oxygen, 1 2 3 4. This is liquid NO-dimeric form, liquid nitric oxide dimeric form, dimeric form, and nitrogen, oxygen, nitrogen, oxygen. This is 1.101 angstrom, 2.38 angstrom in solid state. In solid state, dimeric nitric oxide molecules. This is dimeric nitric oxide molecule. This is the structure of nitric oxide. Okay, nitric oxide. Next, dinitrogen trioxide. Okay, dinitrogen trioxide. Okay, dinitrogen trioxide. Okay, dinitrogen trioxide. Okay, N2O3, dinitrogen trioxide, N2O3. Okay, N2O3 molecule is diamagnetic. Okay, N2O3 diamagnetic. Its structure and basis of electronic configuration can be written as oxygen, double bond, nitrogen, single bond, oxygen, 1 2 3 4, oxygen, single bond, nitrogen, double bond, oxygen. Okay, its vapor density value shows that it exists in dimeric form as its vapor density value shows that it exists in dimeric form is oxygen, nitrogen, double bond oxygen, nitrogen, double bond oxygen, single bond oxygen, single bond nitrogen, single bond oxygen. Okay, in solid state, N2O3 is N2O3 is as NO2 negative and NO positive. Okay, and NO2 negative is nitrite ion. Okay, nitrite ion, and NO plus is nitrosonium ion. NO plus is nitrosonium ion. Okay, nitrosonium ion. Okay, NO2 negative nitrite ion, and NO plus is nitrosonium ion. Okay, then 2NO2 is N2O4, brown and diamagnetic. 2NO2 is brown and diamagnetic, diamagnetic. This is brown and diamagnetic, and N2O4 is colorless and paramagnetic. Colorless and paramagnetic. Colorless and paramagnetic. Okay, colorless and paramagnetic. Colorless and paramagnetic. Okay. Next, colorless and paramagnetic. Okay. Nitrogen dioxide or dinitrogen tetroxide. Nitrogen dioxide or dinitrogen tetroxide. Okay. Nitrogen dioxide. Nitrogen dioxide or dinitrogen tetroxide. Dinitrogen tetroxide. NO2 or N2O4. Okay. IR spectra shows that nitrogen dioxide molecule exists in angular shape. The resonating structures of NO2 molecule is given oxygen, nitrogen, oxygen. Okay. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4 double bond. This is a lone pair. Nitrogen, it is nitrogen, arrow mark of oxygen, 1, 2, 3, 4, 5, 6, and this is oxygen connected with the double bond, 1, 2, 3, 4. R. Nitrogen, double lone pair, oxygen, 1, 2, 3, 4, and oxygen 1, 2, 3, 4, 5. Okay. R. Nitrogen, 1, 2, arrow mark of oxygen, 1, 2, 3, 4, 5, and double bond, oxygen 1, 2, 3, 4. 1, 2, 3, 4. Okay. Actual structure is supposed to be closed in this structure is oxygen, single bond nitrogen, single bond oxygen, 132 degree angle, 132 degree angle, and 1.19 angstrom, and this is nitrogen, and nitrogen single bond 1.64 angstrom, and this is oxygen, and this is oxygen, 126 degree, 1.17 angstrom. Okay. This is the resonance hybrid structure of NO2 and N2O4 molecules. This is resonance hybrid structure, resonance hybrid structures of NO2 and N2O4 molecules. Okay. Fourth point, nitrogen pentoxide. nitrogen pentaoxide, nitrogen pentaoxide, nitrogen pentaoxide, N2O5, N2O5. Okay. X-ray study and Raman spectra show that nitrogen pentaoxide is a ionic solid. In solid state, nitrogen pentaoxide exists in N2 nitrogen dioxide plus ion, nitrogen trioxide plus ion, and N2 plus ion is nitronium ion, and N3 plus ion is nitrate ion. Okay. In solid state, N2O5 exists as NO2 positive ion, that means nitronium ion, nitronium ion, and NO3 negative ion, that is nitrate ion, okay. Then this is nitrogen, oxygen, that is oxygen, 1 2 3 4 5 6, double bond, oxygen, okay, oxygen, okay, and nitrogen, oxygen, 1 2 3 4 5 6, and double bond, oxygen, 1 2 3 4. Okay, this is structure of N2O5. Structure of N2O5. Structure of N2O5. आगे next, structure of phosphorus oxide. Structure of phosphorus oxide. Okay. Structure of phosphorus oxide. Structure of phosphorus oxide. Okay. Structure of phosphorus oxide. Okay. Structure of phosphorus oxide. Structure of phosphorus oxide. Okay. Phosphorus oxide. First is phosphorus trioxide. Phosphorus trioxide. Phosphorus trioxide. Phosphorus trioxide. Phosphorus trioxide. P2O3 or P4O6. Okay. P4O6. Okay. Each phosphorus in the structure has PO 1.5 is equal to P2O3. Empirical. Okay. Empirical and triple bond P4O6 molecules. Okay. Each phosphorus in the structure has PO 1.5, that is P2O3 empirical and P4O6, that is molecule. That is molecule. Empirical, that is molecules. Okay? Hence, phosphorus trioxide is a dimeric, having the formula dimeric. Phosphorus trioxide, hence phosphorus trioxide is dimeric. Phosphorus trioxide is dimeric. Dimeric, having the formula P4O6. In P4O6, P is sp3. Phosphorus is sp3 hybridized. sp3 hybridized. Okay? sp3 hybridized. Electron diffraction data indicates that the 4 phosphorus atoms are situated at the apices of a tetrahedron with 6 oxygen atoms located just outside center of the 6s. The 12 phosphorus oxygen bond length is equal to 1.62 angstrom, which is 1.62. Phosphorus oxygen bond 1.62 angstrom, which is approximately equal to single phosphorus oxygen bond length. In this molecule, phosphorus oxygen phosphorus bond angle is equal to 1.27 127 degree 5 minutes. Okay? And phosphorus oxygen phosphorus bond is 127 degree 5 minutes. And oxygen phosphorus oxygen bond angle is 99 degree. Okay? The structure of a P4O6 you can show the structure of P4O6 is oxygen double bond phosphorus single bond oxygen single bond phosphorus double bond oxygen. Okay? Oxygen have 1, 2, 3, 4, 5, 6. Phosphorus has 1, 2, 3, 4, 5, 6. And oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And phosphorus has 1, 2, 3, 4, 5, 6. And oxygen 1, 2, 3, 4. 1, 2, 3, 4. Okay? This is the structure of P2O3 unit. P2O3 unit, and you can show phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, One, two, three, four. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. 1, 2. 1, 2, 3, 4. Okay? This is the structure of a P2O6. This is the structure of P2O3, and this is the structure of P2O6. Structure of P2O6. Okay. Next, phosphorus pentaoxide structure. Phosphorus pentaoxide structure. Okay. Next, phosphorus pentaoxide. Phosphorus pentaoxide structures. Okay. Phosphorus, oxygen, phosphorus, double bond oxygen, double bond oxygen. This is structure of molecule P2O5. Structure of molecule P2O5. And phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, phosphorus, oxygen, single one connected with phosphorus and the oxygen. Okay. This is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. That is oxygen. 1, 2, 3, 4. And this is oxygen. 1, 2, 3, 4. Okay. This is the structure of P4O10. Structure of P4O10. Okay. Phosphorus pentaoxide. P2O5 is empirical formula. P2O5 is empirical formula. P4O10. P2O5 is empirical formula. Where is P4O10 is molecular formula. Molecular formula. Okay. Molecular formula. Okay. P4O10 is molecular formula of phosphorus pentaoxide. It is dimeric. Having the formula P4O10. P4O10 and not P2O5. In P4O6 each phosphorus forms 3 bonds to oxygen atoms. In P4O10 each phosphorus forms an additional coordinate bond by donating phosphorus lone pair to oxygen. Okay. Lone pair oxygen atom. Bond measurement so that P stands to oxygen, coordinate bond and shorter than a angle covalent bond. Okay. Next structure, phosphorus tetraoxide. Phosphorus tetraoxide. Next is phosphorus tetraoxide. 1 minute. Structure of phosphorus tetraoxide. Phosphorus tetraoxide. Phosphorus tetraoxide. Okay. P2O8 or P4O8. Okay. Okay. Phosphorus tetraoxide is dimeric. This is dimeric. Dimeric, having the formula P4O8. Having the formula P4O8. Okay. In P4O8, each atom forms 3 bond to oxygen atom. Its structure is similar to the structure of P4O6. Okay. Its structure is similar to the phosphorus pentaoxide, phosphorus tetraoxide. Okay. Phosphorus, its structure is same to the structure of P4O6. In P4O8, only 2 phosphorus form an additional coordinate bond by donating phosphorus lone pair to an oxygen atom. Okay. From the structure of oxides of nitrogen and phosphorus, it is clear that the oxides of phosphorus are like cage, while oxides of nitrogen are not like this. This is due to p-pi bond in nitrogen, while the type of bond does not exist in phosphorus due to its comparatively bigger size. Oxyacids. All the elements group 15 form oxyacids by dissolving oxides on nitrogen, phosphorus and oceanic in water. They produce oxy or oxoacids. The important oxyacids of group of 15 you can show. 1 minute. Element formula of oxyacids and name of oxyacids and oxidation. Okay. Element nitrogen elements. Okay. H2N2O2, that is hyponitrous acid. This is hyponitrous acid, that is +1. Next, HNO2, nitrous acid. That is +3. HNO3, that is nitric acid. That is nitric acid. Okay. That is +5. Nitric acid +5. HNO4, that is pernitric acid. Pernitric acid. Okay. Pernitric acid +5. Okay. Next, phosphorus. Okay. That is H3PO4. 2, H3PO2, hypophosphorus acid, hypophosphorus phosphorus acid, hypophosphorus acid, that is +1. H3PO3, phosphorus acid, phosphorus acid, that is +3. And H4P2O6, that is hypophosphoric acid, hypophosphoric acid, that is +4, hypophosphoric acid +4. H3PO4, phosphoric acid, phosphoric acid, phosphoric acid, that is +5. And H4P2O7, pyrophosphoric acid, that is pyrophosphoric acid, pyrophosphoric acid is +5. Pyrophosphoric acid is +5. Next, arsenic element, arsenic elements. Okay. H3ASO3, that is arsenic third. Acid are arsenious acid, +3. Okay. And H3ASO4, arsenic acid, that is arsenic acid, okay, that is +5, arsenic acid +5, okay. Next, antimony, that is H3SbO4, that is antimonic acid, okay, antimonic acid, that is +5. And bismuth, next, bismuth, HbIO3, that is metabismuthinic acid, metabismuthinic acid, metabismuthinic acid, that is +5. This is the oxy acids of nitrogen are the most active, and the strength of these acids decreases from nitrogen to bismuth, okay. Next, Birkeland ID process, okay. Next, Birkeland ID process. What is the Birkeland ID process? First, the most important acids of nitrogen is HNO3, which is manufactured as the most important acid of nitrogen. The most important acid of nitrogen is HNO3, which is manufactured as which is manufactured as manufactured manufactured as first Birkeland ID process. Birkeland ID Birkeland RD process. Birkeland RD process. Okay. Atmospheric nitrogen is converted to HNO3. Atmospheric nitrogen is converted to nitric acid HNO3. Okay. When air is passed through an electric arc at a temperature of 3000 degrees Celsius, nitrogen and oxygen of the atmosphere combine to form NO. Nitrogen and oxygen of the atmosphere combine to form NO. Okay. This combine with oxygen at room temperature. This combine with oxygen at room temperature. Forming nitrogen dioxide. This nitrogen dioxide is sorted. This nitrogen dioxide is absorbed by water and is converted into HNO3. The nitrogen dioxide is absorbed by water and is converted to HNO3. Okay. You can show the reaction N2 plus O2 that make 2NO at 43,000 calories. 43,000 calories. 43,000 calories. Okay. And 2NO plus O2, that is 2NO2 nitrogen dioxide, and 2NO2 plus H2O, that is HNO3 plus HNO2, and 3HNO2 is HNO3 plus 2NO plus H2O. Okay. The reaction N2 plus O2 is 2NO is reversible and endothermic. Reversible and endothermic. This reaction is found by high temperature. Okay. Haber process. Second, Haber process. Second, Haber process. Okay. Haber process. In this process, ammonia is oxidized to nitric oxide. In this process, ammonia 4NH3 plus 5O2. In this process, ammonia is oxidized to nitric oxide. Okay, that is 4NO plus 6H2O. Okay, and NO is again oxidized to nitrogen dioxide. NO is again oxidized to NO2 and 2NO plus O2, that is 2NO2. Okay, 2NO2. Okay, 2NO2. Okay, and NO2 is absorbed in water and nitric acid is produced, and NO2 is absorbed in water. 4NO2 plus 2H2O absorbed in water and the presence of oxygen and make 4HNO3 nitric acid. Orthophosphoric acid is an important chemical which is often used in industries. It is prepared by oxidizing red phosphorus with nitric acid. Okay, red phosphorus with nitric acid. Okay, orthophosphoric acid is an important chemical. Okay, orthophosphoric acid is an important chemical. Which is oftenly used in industries. Okay, which is oftenly used in industries. Okay, is prepared by oxidizing red phosphorus with nitric acid. Okay, phosphorus plus 5HNO3, that is H3PO4, orthophosphoric acid. Okay, orthophosphoric acid H3PO4 and plus 5NO2 nitrogen dioxide plus water. Okay, structures. Okay, structures. 1 minute. Structures. Okay, the structures of oxy acid of nitrogen are, you can show first hyponitrous acid. Hyponitrous acid H2N2O2, that is HO single bond nitrogen, double bond nitrogen, single bond hydroxy. Okay, NT form, that is NT form, nitrogen, double bond nitrogen, hydroxy. Okay, that is synchronous form. Okay. Second structure, nitrous acid. Nitrous acid. Okay. That is HNO2. Okay. Nitrogen, double bond oxygen, hydroxy. Okay. That is hydrogen, nitrogen, oxygen, double bond oxygen. Okay. Oxygen, hydrogen, 0.96 angstrom. Okay. That is 104 degree and 1.46 angstrom. Okay. And nitrogen, that is 116 degree, 1.20 angstrom oxygen. Okay. Third, nitric acid, HNO3. Nitric acid, HNO3. Nitric acid, HNO3. HO, nitrogen, double bond oxygen. That is oxygen, HO, single bond nitrogen, oxygen, double bond oxygen. Hydrogen, single bond oxygen, 0.96 angstrom. Okay. That is 102 degree. Nitrogen, oxygen, oxygen, 150. .22 angstrom, 130 degree, 1.22 angstrom. Okay. Resonating structure of HNO3. This is resonating structure. Structure of HNO3. Okay. Structure of oxy acids of nitrogen. Okay. The structure of oxy acid of phosphorus are shown as you can show. Okay. First hypophosphorus acid. Hypophosphorus acid. Hypophosphorus acid. Hypophosphorus acid. First is hypophosphorus acid. Okay. Hypophosphorus acid. Okay.